Okay, let's start here by reviewing dependent and independent events. Dependent events. Knowing the outcome of one tells you something about the probability of the other. So the probability of A given B is not equal to the probability of A. Now, if they were independent, then the probability of A given B is simply the probability of A, because B has nothing to do with it. It doesn't tell us anything additional about the probability of A. So that's our formal definition there of dependent and independent relating to the total probability, or the unconditional probability, and the conditional probability. Now, looking again at our total probability rule, the probability of A, and this is the example we saw earlier, the probability of A given B times the probability of B. Well, that's the probability of AB, and the probability of A given that B doesn't occur, A given not B times the probability of not B, that's the joint probability of A and not B. So we can just add those up. Now, in that example, we only had two conditionals there, right? B and not B. But we can generalize that a little bit. If we had any number of conditional events, as long as we've got all the possible ones, as we did with B and not B, that covered everything. Well, in other situations, it might not be that straightforward. So we can have a number of conditional events here. And so our conditional events here are S1, S2 through Sn. So this first one is going to give us the probability of A and S1, that joint probability. And so we get the joint probability from each of these, and we've got the probability of A given S1, probability of A given S2. We get the joint probabilities. So if we add those all up, that should be the unconditional probability of A, the probability that A will happen if we know nothing about which S event occurred. So those probabilities of S1 to Sn, they have to sum to 1. So we've covered every possible outcome, just as we did in the simpler example with the conditionals B and not B. That covered all the possible outcomes. So let's look at an example. We've got probability of an interest rate increase, getting familiar by now, 40%. Probability of no interest rate increase has got to be 60%. So if we have these two conditional probabilities, the probability of a recession given an increase and the probability of a recession with no increase, then we can use that addition rule to get the unconditional probability of R. And so again, this gives us probability of recession and increase. This gives us the probability of recession and no increase. Add them together, our 28% and 6% gives us 34%. So that's our unconditional probability of a recession. So if we have no information on whether there's an interest rate increase or not, we say the probability of recession is 34%. Now the concept of expected value. Pretty straightforward. It's the probability weighted average of all the possible outcomes. So for Ron's stores, we've got, what, 1, 2, 3, 4 possible outcomes, and somehow we've determined the probability of each of these outcomes. And so to get the expected earnings per share here, we just take each probability, here's our 4 probabilities, multiply them times the 4 outcomes, add all these up, and that's our expected earnings per share. Now you might notice that according to the model, our expected earnings per share of $1.28, they're never going to happen. If our model's correct here, we've got 4 possible outcomes, and £1.28 is not one of them. But the idea of an expected value is it's our best guess. Given these possible outcomes and the probabilities, £1.28 is the forecast for earnings per share that will minimize our expected forecast error. That's the idea of our expected earnings per share. Now, we calculated variance earlier in the curriculum by taking the deviations from the mean, squaring them, adding them all up, and then we either divided by n for the population variance, or we divided by n minus 1 if we were calculating the variance from a sample rather than the whole population. Now we're going to look at a different type of model and calculate the variance from that. And this is a probability model. So we've got those earnings per share from our earlier example on Ron's stores. And we use our expected value there, $1.28. So we take for each of these the difference between the outcome and the expected outcome. And we square all these. Multiply them by the probability weights and add them all up. Now, you can think of this as when we had a data sample, right? We had n outcomes, n returns, and we wanted to calculate the variance. We divided by n. Well, that's equivalent to giving each outcome the same weight, 1 over n, for all of them. So here, we're just generalizing that a little bit and saying, well, we're going to take the deviations, we're going to take the difference between each outcome and the expected outcome, and we're going to square all those. So that's the same. But rather than equally weighting them now, 1 over n for each one, we're going to weight them with the probabilities from the model. And we get 0.0736. And if we take the square root of that, since we've got sigma squared, our variance, we take the square root of that, we'll get the standard deviation, and that's 0.2713. Now, one thing I should mention here, the units of variance doesn't make a lot of sense because we put in our pound weights, right? Everything is in pounds here. But then we squared those differences. So we ended up, our units are really pounds squared, which doesn't make a lot of sense. But the reason we like to use standard deviation is once we take the square root of that and get 0.2713, we're back to whatever units we put in. So since we put British pounds in as our units, our standard deviation comes out as pounds. If we put in percent returns, standard deviation comes out in percent. Variance, on the other hand, the units would be percent squared. So let's look at another example of using conditional expectations here. In this example, we know the probability of a tariff being put on, and we know the probability of no tariff. And our analysts tell us that the expected return on the market or a particular stock, given that a tariff is imposed, is 15%. And the expected return if there's no tariff is only 5%. So maybe we're talking about a steel company. If the tariff is imposed, their return will be higher. If the tariff's not imposed, it'll be lower. So given all that, we want to develop the expected return. And so it's, again, just a probability-weighted average of the two outcomes. 40% times 15% and 60% times 5%. Add them up, and if we don't know anything about the imposition of the tariff or not, our expected return, our unconditional expectation, is 9%. Now let's take a look at an investment tree and talk about conditional, unconditional expectations and how we can get the expected outcome. So when we draw an investment tree. We start off, we call these nodes. And so the first part is probability that GDP growth will be greater than 3%, and that's 60% probability. And this lower branch of the tree is the probability that growth won't be greater than 3%. So less than or equal to. And the probability of that's just 1 minus 60%, so 40%. So those are our two probabilities. Now we start to look at some conditional probabilities. Given that GDP growth is greater than 3%, that is, we make it to this node right here, given that, the probability of good stock performance, which we've defined as earnings per share of $1.80, is 30%. And the probability of poor stock performance, given that GDP growth is greater than 3%, is 70%. So again, these two branches add up to 100%. And then on the lower branch here, we've got the probability of earnings per share of $1.30, given that GDP growth is less than or equal to 3%, and the probability of earnings per share of $1, given that GDP growth is less than or equal to 3%. So here is our joint probability of GDP growth greater than 3% and good earnings of $1.80 here. So that's 18% of the time. Now just multiplying across, again, we can get the probability of earnings per share of $1.70 as 42%. And following those lower branches, we've got a 40% probability of GDP growth less than or equal to 3%. Given that that happens, there's a 60% chance of earnings per share of $1.30, so that's 24% there. And 40% times 40%, there's a 16% chance, probability, that earnings per share will be $1. So now we have our 4 possible outcomes, and we've got the probability of each. So now we can calculate the expected earnings per share. And that's $1.51. And again, we just multiply each probability times the associated earnings per share and add up those 4 terms. And that's where the expected earnings per share of $1.51 comes from. Covariance is a measure of how two variables move in relation to each other. Now remember, with variance, the terms we used were, what's the deviation of each outcome from its expected outcome? And then we squared it. Well, now we're going to have 2 variables. So instead of squaring that, we're going to take the deviation for the first one and the deviation from its expected value of the second one and multiply them together. So if one variable is above its mean during periods, or tends to be above its mean in periods when the other one is below its mean, we're multiplying a positive times a negative, we'd come up with a negative covariance. If the two tend to move together, then we're either multiplying a value above the mean for one times the value above the mean for another, so 2 positives, or if they're both below their mean in the same time period or the same occurrence, then we've got a negative times a negative. So if they tend to move together, we've got positive covariance. If one tends to be up when the other one's down, we've got negative covariance. And we say the covariance of any variable with itself is its variance, because if it's with itself and both terms are the same, it's the same as we did when we squared those terms and added them up to calculate the population variance. So let's look at an example. We've got a probability model here, and we've got 3 possible outcomes a boom economy, a normal economy, and a slow economy. And our model tells us the return on stock A is expected to be 20% in a boom economy, 12% in a normal economy, and only 5% in a slow economy. And our other stock B, we think it'll do real well in a boom economy with a return of 30%. In a normal economy, we expect it to return just 10%, and in a slow economy, no return at all. So that's our model. So first step, calculate the expected return for each stock. Because remember, our terms are going to be how far is each outcome from its expected return. So for stock A, we've got 3 probabilities and 3 possible outcomes. We calculate the expected value, 13%. So that's our unconditional expectation of the return on stock A. For stock B, we can do the same calculations, our probability weighted outcomes, and see that the expected return, with no information about what type of economy we're in, is 14%. So now that we've got those expected returns for each of our 2 variables, we can look at the deviations from expected returns right here. And so we've got those deviations from the expected return on A and from the expected return on B. And now we're going to multiply those together, and we're also going to multiply by the probabilities and sum those up. So here's the calculation here. So that is column 1 times, or column 1, I guess it's column 2 times column 3 times column 4. Okay? The probability multiplied times the product of these 2 deviations. And we can see those all came out positive here. So I think we're going to have positive covariance, right? So we add all those together, and we get the covariance 0.00580. So similar to the variance, but we did it for 2 events rather than just for the 1. Now covariance is hard to interpret, and we can't take the square root of it and get standard deviation as we did with variance. So oftentimes, in order to understand covariance and what it's really telling us, I mean, we know it's positive here, but do they really tend to move together? Or do they just tend to move together a little bit? It's really hard to tell from just looking at 0.00580. So what we use is something called the correlation coefficient. And it's a standardized measure of the linear relationship between 2 variables. And the standardizing is done by dividing by the product of the standard deviations. Because remember, our standard deviations are in whatever units we used. So depending on how we measured a variable, we might get a very different covariance. But now, by dividing by the product of those standard deviations, this correlation coefficient can take on values only between +1 and -1. So just as a reminder, if on an exam you calculate the correlation coefficient and it's 1.3, you should do that calculation again. Correlation only ranges from +1, perfectly positive correlation. They move together exactly. And -1, perfectly negatively correlated. They move exactly opposite to each other. Now, we use the letter R for the sample correlation coefficient, and we use this Greek letter rho to represent the population correlation coefficient, just like we use sigma for the true standard deviation of a distribution, and we used S for our estimated standard deviation, estimated from sample data. So let's just crunch some numbers. What's the correlation of returns between stock A and B? And we write that, correlation AB. In the previous example, if the variance of returns is 0.0028 for stock A and 0.0124 for stock B. Well, note first off that we've been given the variances here, and we're going to divide by the standard deviations. Okay? So first thing is to get our standard deviations from those variances. So we get a really, 0.0529 and 0.1114. So there's our standard deviations of returns. So we take the covariance that we calculated from our probability model, and we divide that by the two standard deviations, and we get a correlation coefficient of 0.984. Well, now we can interpret that, because no matter how you look at it, that's pretty darn close to 1. So we say there's a really strong, almost perfect positive correlation between the returns on A and the returns on B.